This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
For Software Engineering Radio, I'm Edaena Salinas. Stephen Ewen is a PMC member and one of the original creators of Apache Flink and co-founder and CTO of Data Artisans. Previously, he worked at IBM and Microsoft on data processing technologies. He holds a PhD from the Berlin University of Technology. With Data Artisans and Apache Flink, Stephan works on pushing the capabilities and the adoption of stream processing technology. Stephen Ewen, welcome to Software Engineering Radio.
Thank you. Hello.
There are systems with data constantly flowing through them. This data can come from different sources like telemetry or the Internet of Things. As this amount of data keeps increasing, challenges emerge on how to process it. Batch and stream are two ways in which we can process big data. In a talk that you gave in San Francisco, you mentioned that we can understand these two by asking, what changes faster, your data or your query? Can you explain what this means?
So if you look at the nature of batch and streaming applications, batch applications are applications that take a finite bit of data, and or very typically are applications that take that. And you may want to run different types of analysis over this particular static type of data. Think, for example, of classical data warehousing use cases. You have a static piece of data, which is what is currently in your warehouse, or even if your warehouse is continuously ingested, it's like a snapshot view of it. And then you run different exploratory queries based on the result of the first. Let's say you drill down certain dimensions and so on, run the next query. Another example is like machine learning model training, where you take a piece of input data. You may partition it in different ways, as in like training and validation set, and then you run the training model. But it's in some sense always the same data that you base this on, even though you might split it differently between different training runs. So these are kind of applications where the kind of work that you do changes, but it's always on the same static data set. Streaming is, if you wish, the opposite of that. You have an application that continues to run, and you can really think very broadly of what kind of application that is. It can be something that computes some statistics over what is happening in the data that is being produced. Mm-hmm. It can be like an application like a web service that backs an online application. The logic there is the same kind of logic that runs all the time, but the data that it runs on is actually it's not finite. The data doesn't really exist all before the application is launched. So while the application exists and stays the same, more and more data comes and keeps changing over time. So that's why these two are almost the inverse of each other. And in some sense, that boils down to another interpretation of batch and streaming. You can think of streaming, or the most defining part of streaming is actually this aspect of continuity of data being produced and being processed. A streaming application is inherently an application that is not necessarily bounded towards the end. So while it starts, it doesn't yet have an end of data where it's done, where it actually shuts down and says, my job is done. It just stays there, and it continues to receive events, and events that can come from a message queue, that can come from user interaction with it. Versus a batch application is like a finite job or project. It has a fixed amount of data that you run it on. So the most defining difference is that streaming is unbounded towards the end versus batch is not. And that, with that comes the fact that in batch, because the data is static, usually the application changes more often, and in streaming, because the data is unbounded and the streaming application exists before you even know the end of the data, the application usually stays the same while the data changes.
Are there characteristics of the applications that is better if we use the streaming approach? Because in a sense, we can have this stream of data coming, but we can just decide to store a big file and then just do batch processing. What is the advantage of having available this technology of stream processing for certain applications?
I mean, stream processing has a bunch of very strong advantages, which is, I think, why it's actually creating such a big interest at the moment. The first one is quite straightforward, right? If you ingest the data first, wait until you've filled up a certain chunk, and then say, okay, let me take this static piece of data and then run a batch job. You're introducing a delay until you actually run the computation. So for the time that this amount of data, this buffer or this block fills up. So if you're this results then often in this periodic batch jobs. You ingest for a while, and every day, every hour, every few minutes, you kick off a certain batch job. But it inherently actually means that the data is already a little bit stale by the time the computation runs. And a lot of data is very valuable when it's very fresh. So the getting this delay down is something people are very interested in. And I mean, the best thing you can actually do is get it to zero and just process it as it comes, right? Mm-hmm. We've seen this trend of periodic batch jobs trying to become more and more frequent, so they act on fresher data all the time. And then streaming is like the extreme form of that. You don't even try to chop it into finite sets and then run the batch processing application, but you just process the data exactly immediately as it comes. That is one part of it. Stream processing really helps with immediately reacting to data when it's still very fresh, when it's very valuable. And for a lot of application, it doesn't even make sense to react to certain events anymore in hindsight. Mm-hmm. The other aspect to that is that streaming is really a very natural way to represent a lot of problems. If you look at how most of the data is produced, it's actually produced in a continuous fashion, in a somewhat unbounded fashion, right? Streaming data, treating a problem as a streaming problem, matches that very well. If you look at the data producer, like a web service that just logs user interactions, and you want to process that in order to get insights in what is happening in your service right now, or to build like a live recommender. Also, the interactions being continuous produced over time is really a stream. And if you try to apply batch processing to that, you come to this point of saying, okay, so this thing that is actually created as a stream in an unbounded fashion, I now have to introduce arbitrary boundaries, and then interpret each individual carved out piece as a finite data set. It's actually not as natural a thing to do as just treating it as a stream and processing it as a stream. And I think it's mainly been done historically because of immaturity of stream processing technology. There was just no other way than to say, let's cut the stream into pieces and treat each piece as a batch. But as stream processing technology continues to mature, we actually see that a lot of people are very interested in again adopting this quite natural paradigm of processing a stream as a stream.
Mm-hmm. Let's talk a little bit about that. You mentioned batching was in part used because stream processing was still immature. So I just want to understand if there's somebody that has all this data coming from the web service, like you mentioned, and they want to set up batch processing. What would be the components of this architecture? For example, where can the data be stored? Would it be like a distributed file system? And just pretty much what would they need to do to set it up? as closely as if it were stream processing, but not quite there yet.
I think if you look at the somewhat historical evolution of technology, I think this actually goes back quite a bit. You can see that, with relational databases, people have tried to do the same thing, right? Continuous ingestion, or as data is produced, you immediately insert it into the database, and then you periodically run your analytical queries on the database. This is a form of like streaming ingestion into a store and then running batch processing just within this like all closed monolithic piece of the database. And some companies have actually adopted that long ago, and like somewhat successfully, even if at quite significant costs in many cases. But I guess if you look at the more modern trends, the big data way of doing this, it's probably more like you said, right? You have something like a continuous ingestion into a distributed file system, with projects. I guess the first ones to do that were projects like Apache Flink or so, and then you would have something else that kicks off the batch job that analyzes the data in the distributed file system. Yeah, so for streaming ingestion and then batch processing to approximate stream processing, I think that would probably be the approach. And if you're trying to approximate stream processing more and more, you end up at trying to decrease the batch size more and more until the batches become just very, very small, and you might end up with something like mini batching even.
So you mentioned like in the very early days, it was just a matter of setting up a database related for gathering the data and just adding the data to a table or something and then processing that. And now we have distributed file systems with Apache Flink. What are some of the bottlenecks? So
Flink was one of the very early technologies. I think probably these days, if you ingest into a file system, there's very different ways to do this. It's either you actually use a stream processor directly to ingest into the file system and do some, if you wish, some pre-processing on the way, or you may use things like tools that work with the message queues and directly write from message queues to the file systems, like tools around things like Kafka, or also like Event Hub or PubSub and so on. A lot of them come with connectors that are like mainly intended to do ingestion into batch processing, because it still is a big use case.
I see. So what you're saying is that the one where you mentioned that is just Apache Flink and a distributed file system, like it's still pretty in the early days if you try to do that now.
I think these were the early days of taking streams, putting streams into a batch storage and then computing over the batch storage. Yes.
What were some of the bottlenecks that could be hit back then if you're trying to go with this approach of doing batches more frequently as the system keeps growing?
I mean, a batch job, depending on how you set it up, often has a problem of, I think you can call this like broken boundaries. So let's say you have a batch job to analyze sessions with which users interact with a certain service. That's very often something you need at the beginning, right? You just need to actually gather user sessions and gather like a user's behavior within that session, and that is input then to some later processing step, like like training a model to predict what users would be interested in depending on what they interact with. The problem is if you actually chop your data stream, at some point you're inevitably going to break a lot of these sessions, right? So you have to put some logic in place to kind of repair the boundaries, to carry some results from the previous batch also into the next batch. In that way, trying to carry the in-progress sessions into the next one. If you start decreasing your batch sizes more and more and more, you can easily come to the point that each batch does way more. It just either repeats a lot of work, or it has to spend a lot of work like carrying over information from the previous batch. And you almost come to the point that warming up the actual computation is much more effort than the computation. And that is where, if you actually come to the model and say, yeah, let's actually just treat the computation as continuous. We just, we keep the information, we keep the state in there all the time and just continuously compute on this, just forgoes all of these problems.
I see. And the ones that you highlighted is the batch is essentially just one piece, but because you're doing them smaller and more frequent, there's this additional steps of stitching together previous information and using that for the current computation is what you're saying, right?
Yeah, this is just in order to, let's say, if you want to approximate like more closer real-time computation with batch processing, there's a lot of applications that have the requirement to just operate with a very low latency, where it's completely infeasible to even start up the batch processing job within the time that they usually need to deliver the answer in, right? So a lot of fraud detection, anomaly detection, like network intrusion detection and so on, where you really have to answer within like sub-second, often even sub 100 milliseconds and so on. It's completely infeasible to like first do the ingestion and then kick off the batch job. For these applications, it's really essential that the computation is online and immediately reacts to the data as it comes in. But even for applications that don't have this like very hard low latency requirements, if you start to make the batches shorter and shorter and shorter, at some point in time, you're paying a lot of overhead price in be that with scheduling, be that with loading, pre-warming, preloading, like previous results and so on, in order to continue on them.
You mentioned if you have a system where you value data that is fresh, like for example, fraud, anomaly detection, or intrusion, that's a point where you can switch to a stream processing architecture, because the architecture with batching, even if you do it more frequent, we talked about some of the issues with that, but there's a cost issue where costs can get very high. At what other point?
I think there are many cases where you actually want to switch to that before actually coming to this like very, very low latency case. Like I said before, like streaming is really a very good paradigm every time the data that you're processing is really continuously produced data, and you have this kind of piece of work that is the same work that you apply to all the data, right? Be that routing it to a different point in your infrastructure, like ingesting it into storage is one example of like a continuous piece of work that you do on changing data as it changes over time, but also indexing it, filtering it, pre-processing it, searching it for anomalies, continuously updating certain models or certain state that you keep around for, let's say, for users that interact with your website, or for other customers. All these things that you tend to do continuously all the time, and that work on data that is continuously produced. Like this, these are natural streaming applications actually. And even if they don't require a super low latency case, there's really, with maturing stream processing technology, there isn't really a reason anymore to not treat them like that. The reason to treat them with batches, I think, were mainly historic, when batch processing was vastly more efficient than stream processing was. But that is not quite the case anymore. So there's really a very good point to start like just treating streams as streams and modeling the processing as streaming applications.
I see. So you're saying if you have a component that's continuously generating data, that in itself is enough to switch to streaming. What about a scale? Is there a certain scale where we should start thinking about stream processing, or just with the idea of we have something continuously being generated, let's just wire up a stream processing architecture to it?
I think in many ways, as soon as you have this continuous data, continuous processing, continuous computation, this is a good reason to actually start thinking about a streaming architecture. So we see users, like from our perspective, users of Apache Flink that use stream processing on as many nodes as like 1, 2, 3 nodes for very low volume data streams, or as many as 10,000 nodes for extremely high volume data streams. So the technology really works on very small scale and very large scale, and it is really all about modeling your problem or modeling your application as a stream processing application. That's something that does continuous processing, versus a certain scale that says, oh, at this scale I should really go rather for stream processing, versus at that scale I should rather go for batch processing.
Earlier, when we were talking about very early days architectures, you mentioned that one improvement, particularly in the batching one, but it can still be used for streaming architecture, is this pub sub and message queues. Can you explain what PubSub is?
If you look at data being like streaming data being produced and being made available for processing, it's very often quite beneficial to decompose the stream processing part and the data producer part, and put the data somewhere where it can be consumed in a streaming fashion. But it can also be buffered there for a while. It can be reconsumed in case we have a failure in the application and need to redo a little bit of work. And these systems that are somewhat there, you can think of them as being the equivalent of the distributed file system in the streaming space, where the distributed file system are the storage for batch. These systems are the storage for streaming. Those play the role of being very often the first ones to receive the data and to buffer and store it, at least for a certain while. And those are very often either pub subsystems or logs.
I see. So what you're saying is one way of structuring the streaming architecture is to have this section that handles data producing, and this other piece that's more about the stream processing part. And that in its sense is the PubSub. You're publishing the data, you're producing it, and the sub, which is the subscriber, is just taking that data and doing some computation of it. So at a higher level, there's two main pieces in a stream architecture, right?
There are two main pieces. I would say probably more if you look more towards the edges, and I think they're interestingly very analogous to the pieces of a batch processing architecture. In a batch processing architecture, you have batch storage, like a distributed file system. You have the batch processors to do the computation. You often have a piece that does the the data ingestion, and you often have something that takes the result of the batch processor and does something with it, either continues it to push it down the further downstream steps of the workflow, or presents it in the form of a dashboard or something like that. And in the streaming architecture, that's really very similar. They're the producers. The producers typically write into some form of log or message queue, which is the storage piece, and at least the, let's say, short-term storage piece, short to mid-term, depending on what exactly you use. And then there's the computational part, the stream processor, which is the analog to the batch processor. And then you usually have some form of system that takes the results and does something with it. The system, and the results can be really anything. The results can be actions that are triggered in the infrastructure by RPC, or dashboards that present real-time analytics, or just be storage systems or other streams for downstream consumption.
I see. And you mentioned the message queue is short-term storage, right?
So the way that most of these, let's say, message queues or logs work these days is that they have kind of a limited lifetime. There's some projects that try to work around that, but I think the state of the art, the popular projects, all have a limited storage time or limited storage capacity. So when the data first goes into the log or into the message queue, it stays in there for a while for various applications to consume. And there's very often one of these applications that consume the data is very often, you can think of it as some form of backup application that takes it, maybe filters it, compresses it for some form of long-term archival in some form of bulk storage, like again a distributed file system. This makes in many ways sense to use the distributed file system there, because at this time, when the data actually is accessed from there, it's no longer fresh data anyways. So it's not really important to serve it from a message queue. And there are projects that try to combine these pieces, message queues that age out data to distributed file systems automatically.
And when data reaches this message queue, has it previously undergone a transformation, or is it just directly putting the data the way it was formatted, for example, for a log? Or is there a step prior to that?
So when the data hits the log or the message queue, the logs and message queues are really the are the data storage both for the fresh, let's say the initial raw data as it comes directly from the producing service, but very much also for the data that comes out of the first pre-processing steps. So very many setups that we see have a log or a message queue just for the raw data stream, then have a stream processing job that does initial filtering, transformation, cleanup, enrichment, and then writes it into multiple other message queues and logs for different downstream consumers. And then, there may be different consumers that do some other massaging of the data and write it again to a log or message queue for even further downstream consumers. So it's really, in the same way as one batch processing job can write a result to the distributed file system, and then the next batch processing job can pick it up from there. In the same way, stream processing jobs can pull their source data from a message queue and write it downstream to a message queue again.
What's an example of a piece of data that reaches the message queue, just to illustrate what are some of the things that can be logged by systems? We can talk about it in terms of that web service system or the anomaly detection or some other application.
So it can be really almost any event that reflects something happening, right? It can be machine generated events. So for some use cases that we see, it's actually just servers reporting or microservices reporting what they just did, and it's just used for to maintain metrics of what is internally happening. It could be something like a credit card transaction that hits the message queue, as in, okay, somebody is trying to do this transaction, and the streaming application now computes let's say a risk score. Do we believe this is a fraudulent attempt or is it a valid attempt? It can be a user hovering over an item on the website, which feeds back into the message queue and into the stream processor that then updates the user's behavior model, which is again input to the website computing what to show next, like which product to suggest next or so. It can be an event generated by an app like a geo coordinate that goes to the message queue and the stream processor consumes the stream of pings with geo coordinates to actually try to compute traffic models of a certain region. So it's very broad what it could be.
Let's talk about the next step in the architecture, which is the computational component. When we're dealing with streams, how can computation be done in this continuous data?
So in some sense, there's like the first piece is very simple. An application that just reacts to events is an application that just either receives events being pushed their way, be that as being a reactive application, as reacting to RPC calls even, or something that just pulls from the message queue and does something with the event. And like this kind of simple case, I think has been around for a while. The tricky piece is, how do you implement a system that computes over these events? Does that in a very consistent way, like in a very fault tolerant way? Let's assume the simple case, we're reading from a message queue, doing some computation and writing to a message, making sure that whenever something fails, we do not actually accidentally do repeated work, like we're not publishing an event while we recover from the failure that we have published before, that can create wrong results downstream. And the even more challenging part is, once we're not looking at this in a stateless fashion anymore, once we're looking at applications that take an event, but they can't really look at the event in isolation, they need to understand the context. Let's say the event represents a user interaction. They need to have the context of what were the other interactions that the user did before, in order to model its session behavior. Or if the event is a credit card transaction, and we need to take other contextual data into account, like what other transactions are ongoing at the same point in time, let's say between the same source and target accounts, or what was the other previous behavior of the user, for a certain type of transfer. Whenever we need this contextual information, and it very often is not just like reading this contextual information from some auxiliary database, but taking the event, processing it with the context in mind, and also updating this contextual information. Whenever we have this kind of pattern, we talk about like stateful stream processing here. And like this is really the much more challenging part, because what you can think about is all of a sudden this computation now has both the role of the computation and of data consistency in some way, right? Because they're maintaining the state of the application, the contextual information for each individual request that the application processes in conjunction with the computation, and maintaining a big consistent view on that without sacrificing like performance and scalability. That has been, if you wish, like the grand challenge of stream processing over the last years, and the like efficient solutions to that problem are what I think made stream processing technology really take off.
So this computational component is the one that would have that logic for gathering the context. Is that correct?
I wouldn't call it gathering the context. If you do stateful stream processing, think of it as you're just some application that some programmer wrote in, be that Java, C#, C, Python or so, and you're handling a bunch of events happening. Somebody sends you an event, calls a function, and you're just treating this, and you're trying to also maintain the context. And you'd probably have some local variables where you store, okay, I've seen so many events for that user, let's say in the last minute. I've seen so many events of that certain type in the last day, and so on. Something that you'd store it in a local variable. If you just build a very simple standalone application. If you then, of course, try to make this fault tolerant, like an application that can handle failures, that can recover, that is resilient, then very often you don't store this in local variables anymore, right? So what you do is you try to connect a database, and you say all these things that I need actually to be able to recover. I store them in the database. So whenever an event comes, looking something up in a database, doing some computation, and writing something back in the database. You may not do this explicitly. It may be hidden from you by frameworks that do that in the background. But in some sense, that is what happened for most applications that just reacted to events, to real-time data. And the big thing about stream processing is you don't have this anymore, the separation of computing and storage, but you have actually a stateful computational component that does this computation and state management consistently together for you. So it's really a rethinking of the whole architecture of computation and state management. And this has both big implications on real-time data processing, because it is much faster than talking to a database in the background. It's much faster than if you talk to the database in the background. You're almost back to the original architecture of events come, you ingest them in the database, and then you try to compute something with either if you compute in real time, you may have to find some triggers on the database or so, or you frequently run queries. But instead of doing that, you really let the application directly handle the data, and the streaming application then has to worry about the fault tolerance and the recovery and consistency of the data. And the stream processors giving you the like the building blocks that take this hard challenge, that solve that hard challenge for you to actually do the consistency and persistence and recovery, and in the same way also the scaling out and scaling up. That is really the core of stream processing technology. And we talked a lot about like applications and databases, and this is also where I think this is where this is starting to make a big impact. It has started to be something more than just a faster way or a more low latency way of data processing as we do it with batch processing. It's actually started to become a different way of building data-driven applications, rather than having like a stateless application server that talks to a database whenever an event comes, whenever a user sends a request or something like that. You really fuse those two things together into a stateful stream processing application that reacts to like the events coming in the stream and manages the state itself.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
Yes, I really see the value of adding this state part to stream processing, particularly in the case that you mentioned about credit card transactions or taking into account what else has the user done before. For the stateless one, I just want to understand what would be an example where it wouldn't really matter to take this context into account.
I think very simple examples of stateless applications may be, stream processing applications that just route data. So you're receiving a raw data stream, and let's say for every event that comes in the raw stream, you're let's say filtering it, re-encoding it, and you're writing it to another message queue downstream, and maybe writing a copy to the distributed file system storage for archival. In this case, you really treat each event individually. You don't need to know any contextual information across events. These applications are pretty much stateless. They may maintain, like a minimal amount of state in the sources and sinks to coordinate, like avoiding duplicates on recovery, but that is more like implementation specifics on how the consistent integration with the source and target systems works. The core application itself doesn't maintain contextual state. So things like streaming real-time ETL, where you don't pre-aggregate, but you really only filter and transform. That would be an example.
What I'm trying to understand is, does data from different parts of the application end up in the same message queue for processing, even if it's not very related to each other? For example, we have the credit card transactions information, but we can also have data about user behavior in our web application or something like that.
I think in many ways, the setups we see use very similar, like logs or message queues for these events, because there's not really a need to treat them differently, right? And like in a first order approximation, they're just all bytes that describe something that happened and that carry that information, and also their availability should trigger something, right? These are the two main components of an event: carry some information and it triggers some action, and all of them exhibit that behavior. What exactly their purpose, their meaning is for the rough architecture, that doesn't really make any difference. No.
You're one of the founders and creators of Apache Flink, which is an open source stream processing framework. Can you explain in more detail what it consists of?
Yeah, so Apache Flink it's a pretty broad system these days. It has grown a lot. It is in its core a system to do exactly what we said before, to compute over data streams in a stateful fashion. That's basically its core mission. Now, Apache Flink takes a very broad interpretation to that. So over the course of this discussion, we talked about batch processing, we talked about stream processing as faster batch processing, faster analytics. We talked about stream processing kind of being a model to create applications. And Apache Flink really tries to take this very, very broad interpretation to what stream processing is. Stream processing is the unifying paradigm to do any form of continuous analytics and to do continuous applications. And it for example interprets batch processing as a special form of stream processing. Stream processing is computing over an unbounded amount of data with continuously existing logic. But in some sense, batch processing is a bit of a special case of that, just right. So instead of having an infinite data stream, you have a finite data stream. That is your finite data set. And whether the application actually continues to run for long or short, and then you start another application, doesn't really matter to Flink. So in that case, it actually does batch processing as well. And it actually it doesn't just look at batch processing as only doing stream processing with slightly different parameters, but it also has certain optimizations in the system for like assumptions that you can make if you work on bounded data versus unbounded data. For example, you can do different forms of scheduling. You can use different forms of data processing algorithms if you know that you're working on unbounded data. It gives you the abilities to Flink gives you very much the abilities to model stream processing in a highly flexible and expressive way. So one core part of stream processing, of building stream processing applications, is treating of data completeness and latency. I think you can think of it like that. If you only look at batch processing, in batch processing you have a fixed set of data and that is all you ever have, and you have it all at once if you wish. In stream processing, data comes continuously, and for a lot of results, there's this trade-off. Like, how long do I wait for my result? It might be a little more accurate if I wait a little longer. If I want to, let's take the example of some mobile application that sends event into our engine, and these events might they might be affected by some transport problems or so, coverage issues. They might not be sent all immediately, but they might be sent in bundles in order to save some data. And then when you actually do analytics, at any point in time, you can say, let me wait a little longer, and I can take a little more data into account to really understand what happened within this hour, because some data might still be late. On the other hand, you might not want to wait for long because that would hold back your results. So this is one of the absolute core elements of I think real-time data processing in general, where stream processing in Apache Flink gives you really good tools to model that. So this is the very core of Flink, right? Continuous streaming, really embrace the nature of all the streaming questions, giving you the right tools to model the application. Doing batch processing as a special form of streaming, doing stream processing, very robust, very scalable. Flink powers some of the largest stream processing setups in the world that we personally actually know of. And it tries to also innovate in other areas, like, for example, how do you specify stream processing applications, right? You can specify them as applications in Java, Scala, and Flink, but there's also very active development on a layer for streaming SQL. So it kind of comes with an interpretation of what SQL means in the streaming world, and a very powerful implementation of SQL that actually has a very consistent meaning between the batch world and the streaming world, but still comes with certain extensions or built-in functions that make a lot of streaming use cases very well representable in SQL. So it's really, Apache Flink is this big project, computation over data streams at the heart, and then all the things around it that you need to model the applications with different APIs, with the right tools, and spanning the whole breadth of the spectrum: batch processing, continuous analytics, continuous data-driven applications.
What does the tooling look like for what you talked about just now, where you're trying to determine at one point do you stop and provide a result when, like you said, you might need just a little bit more data to produce something meaningful? I just want to understand, in what ways can users specify this, or does the system determine that part?
This is basically the core of the event time model that Flink implements, which is highly inspired by the data flow model from Google and Apache Beam. The core part of that is, first of all, making the switch from what is called event processing time to proper event time. So events are interpreted by the time that they were created or stored. They're not interpreted as belonging to the time that they're processed in the stream processor. And that is actually not a big deal if you think about it, right? This is pretty much like in most batch processing systems and in SQL. There's a field in the event that's a timestamp, and in order to compute what has happened per hour, you sort of round the timestamp down to the full hour and group by it. So like having first-class support for that in the stream processor, it just makes sense, especially if you also look at batch processing as your use cases, right? The interesting part is when you have that and the stream processor is very aware of this timestamp that is important. It's not just something that's hidden from the stream processor. It has to be aware of that time. Then you give the user the way to define a like what we call watermarking strategy, and that really encapsulates this trade-off between latency and completeness, right? You can think of the watermark being the point when you say, okay, my data is now complete, heuristically complete, and I want to act on it now. And how aggressive you define this to be, depending on like the characteristics of your data stream. This really encapsulates the trade-off. That is one part. Another part is for example, that Flink offers like a very flexible programming abstractions to interact with, like with timers that are triggered by either clocks or watermarks and so on, in order to allow you to say, okay, I'm acting on data, I'm acting on, let's say, on watermark, but I'm also acting the latest at this particular point in time. You can take events, you can schedule them to be reprocessed later, for example, when you have a bit of a more complete view of your data, and all those tools playing together is basically the toolchain that you have in order to model this behavior between latency and completeness.
I see. And if I understand this correctly, you mentioned event time and event processing time. Event time would be the one right when the data is generated, right? By an IoT device or something.
In some sense, it is whatever time you assign the event initially. It's
okay.
Quite often when the event was produced. It might also be the time when the event, hit the gateway server. It might be the time when the event was first written into the message queue. It's whatever time you assign the event. The important thing is it has to be a stable time, and it should reflect something about the event, not about when you launched the job that processes the event.
And the processing time, would that be when it reaches the computational component like Flink, or it can also...
Yeah, the processing time is really pretty much wall clock time, when it is the time when it reaches a specific operator. And in many ways, the applications, let's say if you just want a simple application, you might be completely okay with just saying, I'm aggregating my events in Windows by event time. I have a watermark that is either perfect because my event stream is decently well behaved and I can encapsulate that in the watermark generation strategy, or I have a heuristic watermark, and you're done. This is what produces your output results. And if the watermark falls a little behind and the latency increases, it's okay. You're dealing with that. If you're doing very sophisticated applications that have like very hard real-time requirements, you very often take processing time into account and say, okay, I also need to take into account that if event time, if the watermark signaling me reasonable completeness, if this actually takes too long, I actually want to act anyways, just based on a local clock. When the event first comes, I may say, defer to later, to when the data is more complete, but also no longer than 100 milliseconds. In this way, you kind of combine both notions of time in order to create something that trades off completeness and latency.
Earlier, you mentioned that another part that you're working on in Apache Flink is defining what SQL means in this context. What I'm curious of is you work with, Flink has been used by clients like Netflix, Alibaba. What are examples of queries that can be done to streams?
So let me take back a step to answer that question. So the interpretation of SQL in the streaming space is actually is a really kind of I think a bit of a newer thing. It's so Flink the Flink community is very much cooperating with the Apache Beam community and with the Calcite community to define that. And in our model, there is SQL is inherently defined on tables. So let's actually, streaming SQL should also be defined on tables, but exactly in the way that, classic SQL is more like batch workload, the table is viewed as a static, as a fixed thing. Streaming SQL takes a view of the table as a dynamic thing. It's a table that changes over time. So the result of a SQL query that goes over a static table is a static table, and the result of a SQL query that goes over a dynamic table is again a dynamic table. And the semantics stay pretty much exactly the same. It's actually a concept that is somewhat hidden in some databases in the form of materialized views and materialized view maintenance in some of the more advanced data warehousing databases especially. And we kind of take this as a base semantical model for streaming SQL. The question then becomes for kind of threefold. How do you derive the dynamic table from a stream of events? How do you turn the result dynamic table into a stream of events? This is kind of the question. How do you connect to the outside world? And this is where users have quite a bit of flexibility to describe how to derive the table and recreate streams from the table. And then inside SQL, it's all about which computations can actually work efficiently on changing tables to produce a changing table, right? You don't want to recompute the SQL queries work every time a change to the dynamic input table happens. We can theoretically do this, but it's not going to be very usable at any non-trivial scale. So in some sense, all workloads that lend themselves to this incrementalization, so you can dynamically compute the results based on changes of the input, those are very good fits for stream processing. Concretely, there's a lot of queries for which that makes sense. Some of them are not yet possible in Flink, especially if it comes to the point that they use very complex forms of, let's say, subqueries and correlated subqueries that the optimizer cannot rewrite. Then there's no good efficient way to incrementally update the results. So those don't lend themselves for streaming SQL execution. But we've actually seen that within the some of the bigger users of Flink, like Alibaba, like Uber, Yelp and Lyft, there's a lot of the use cases they have for stream processing actually match SQL pretty decently. There's a good mix. There's some very kind of advanced special applications that they implement directly, let's say on the more low level streaming APIs to really exploit very specific capabilities of Flink. Very often these are also the heavy lifting jobs, the ones that run at a very large scale, that do something very specific and important. But there's the bulk of applications that do some processing, that contribute to some service, that actually are a pretty good match for SQL. So I wouldn't go to the point to say, SQL is all you need for streaming, but it's probably a good 80-20 principle there. You can probably, with a good SQL support, capture 80% of the common use cases, and then 20% you offer to actually go down the stack to a more low-level API, which gives you better control of what happens.
When I was researching for this interview, I saw that Apache Flink has 3 abstractions. We've talked about 2 of them, the analytics component. We also talked about stateful applications. You mentioned right now the other abstraction, which is more of the low level that explores specifics of Flink. Can you explain a little bit what this means, this low level abstraction?
So one thing to maybe point out at the beginning is these are in some sense, you can think of them as slightly different abstractions, but they all kind of blend together or interact very well, right? Mm-hmm. So a single program can actually use all of these together. You can start out in SQL, and then you can say the result of this dynamic table I converted to a data stream. Then I do some operation on classical data stream, windowing, some computations, and then I'm using some more low-level piece that gives me more raw access to state and time. I guess the APIs that you were referring to were really the streaming API versus the low-level process API. And actually from Flink, if you look at the Flink code base, they're really within the same API. The lower level piece is just something that exposes a little more the raw ingredients on which other operations are built. So if you think of streaming as as a processing paradigm that takes a stream of events and then treats a lot of events together. For example, by defining things like, give me the average time a user interacts with this service. Like you build a user session, you compute how long this is, compute the average. Let's assume we're computing this in the data stream API, not in SQL for now. This is really a bit of a computation where you don't look all that much at individual events. You're really looking at all these events together. You're more thinking about the stream as a whole. The more you actually go to like a very complex application with sophisticated business logic, the more often it is actually the case that you receive an individual event and you're doing very specific logic depending on this individual event. So, for example, based on the type of the event, handling it differently based on some fields of the event, treating it immediately or deferring it to later or so on. And this is what this lower level abstraction gives you, right? It gives you a nice way to say, give me an event, give me access to time. So give me access to time, meaning let me actually understand what is current processing time, what is current event time. Let me schedule timers that call me back when a certain event time has been reached. Even taking the event and putting it in such a timer and say, just give me the event back actually when a certain event time has been reached. A very raw access to interact with state and so on, rather than state being implicitly handled by windows and window aggregates and so on. This is more the low level abstraction. And if we actually look at the use cases of Flink, we've kind of seen things. Kind of the more you're doing analytics, the more you gravitate to the, let's say, data stream or SQL API, and the more you're building data-driven applications, the more people tend to gravitate to the low-level API, to the very raw, access to event processing time and state. That seems to be a pattern.
To get more customization in that case is one reason, right?
To get more customization of the pipeline as a whole.
Yeah.
Exactly. But yeah. The more you deal with applications, the more you worry about the individual event. And I think the more you deal with analytics, the more you're really looking at groups of events, windows of events. There are individual steps like filtering and event transformations or so on, that where events can be transformed individually or so. But like the big picture is you're really interested in the sum of events rather than very custom logic per individual event.
The last question that I want to ask you is about the next wave of stream processing. What are some of the areas where you see architectures evolving, stream computation evolving?
I think there's various areas where stream processing is still evolving. Like on the application API side, I think SQL streaming, SQL still is actually still evolving in itself, even though the model, the semantics, the definition is actually quite simple and quite complete in itself. If you actually look at how do you make this usable for a lot of common use cases, there are a bunch of constructs you may want to add, and you can actually add them without, possibly by extending the SQL standard, but possibly also by using certain crafty ways of using the existing SQL standard, masking them as UDFs and so on. There's a bit of work, for example, we're doing in Flink in order to get typical join and enrichment semantics that are very common in stream processing feel very natural in SQL. So on this application API layer, there's quite a bit of work. A piece of work that somewhat related to that we did outside Apache Flink, that the company that the original creators of Apache Flink founded, Data Artisans, that we're working on is actually we've built a system for, you can think of it like running distributed asset transactions over streaming data, transactions that take not an individual key or so into account or an individual row, but really like a multi-row view. It's without diving into the details, it's a little bit like opening up stateful stream processing from the capabilities, let's say, of compute plus a key value store to compute plus a relational database, which is quite a bit more powerful. I think this is a very interesting direction also in which stream processing still can develop. Going back to the open source, to the work in open source in stream processing itself, one thing where stream processing is still where there can still be today a reason to use batch processing rather than stream processing is, if you wish, resource efficiency, because batch processors still tend to be a bit more dynamic in their resource utilization. They schedule more fine-grained tasks on finite pieces of data, which in many setups leads to fewer resource consumption compared to like long-running streaming jobs. So there's quite a bit of effort going in the Flink community to introduce more in like automated scaling, automated adjustment to resource needs. I think this is going to be one of the last big things where batch processors have a certain like advantage over stream processors. There's a whole lot of work going in providing a more unified view of batch and stream processing. While the data flow model suggests a really good way to do this in the APIs, there's still quite a bit of work needed, I think, on the storage side and on the runtime side to get this really unified behavior that, stream processors, when they work on historic data, even if they're not really put into a batch mode, they can still exploit some of these advantages of bounded data. And then finally, there's always the work to make things like more scalable, faster recovery, zero downtime upgrades, all this work that becomes interesting once you actually say, hey, we have the stream processing technology that actually is a really cool way to build applications. Let's now build really highly available, highly critical real-time applications with that, and the characteristics that you actually need once you start doing applications that need a lot of nines of availability.
Stephan, thank you for taking the time to come on the show. It's been great talking to you.
Thank you very much. My pleasure.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SE-radio. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.